first of all, to the organizers for inviting me here. Special thanks to Ben Paul for providing a laptop, especially for shortening down this talk. So I think I should start by explaining where I come from and why I have this funny triple affiliation on my badge. That's because I'm working nowadays in the Physics Competence Center of the BASF, so corporate research. This is in fact 2 by 7 kilometers. It's the largest chemical plant in the world. Yeah, so the city is about that size, and this is the plant. We are 700 PhDs in research, so it's like a university of its own. And so nowadays I'm mostly working on self-assembly, organic, inorganic systems, also some protein work. I still have the side activity in femtosecond spectroscopy. We have a lab of that kind. But today I report on stuff that was done in the Max Planck Institute for Quantum Optics in Garching, and that was then pursued further in Marburg, which is a small German university town, at physical chemistry there. So, I will give you an introduction to both the system that we are treating and to the methods that we apply. I'll then show you on a phenomenological basis what we achieve, what kind of control we can achieve in light harvesting. I'll then show you 3 approaches how to understand this and how to get an idea of what the mechanism is there. And finally then I'll link this to this meeting and some more. Carotenoids have been appearing in this meeting already. So what is essential here is we have a pi conjugate system that extends over some number of alternating double bonds indicated here. So natural carotenoids go from 9 to 13 double bonds. Beta-carotene, that's what is good for your eyes. It comes from the carrots. Zeaxanthine is essentially the same. Lycopene is linear. So you see that the conjugate region ends here. This comes from tomatoes. Rhodopene glucoside is the one that is essentially in LH2, so in the light harvesting complex 2. And the one when you want to do spectroscopy, what you can do is you look at mutants of the system. So you compare different carotenoids. For instance, you compare the one that's sitting in LH2 and the one that you can look at in solution, the lycopene. Or you can make artificial systems, and I'll show you that have especially long or especially short conjugate regions. As an alternative to that, we do mutants of the spectroscopy. So normally what you do is you have one excitation pulse, hits the sample here at the intersection point, and then you have a weak broadband probe pulse that goes into the spectrograph. So you look at the change of the color of the system over time. What we can do now is we allow the excitation to be shaped, so to be not a single pulse, but to be a complex pulse shape. It can be a simple pulse shape, just another strong pulse that may be tuned to some excitation energy. And I'm relying today essentially on the ChemPhysChem, which is also in the program here. So these are purple bacteria. They use light harvesting for phototaxis, so for knowing where to go. And if you scan a bit further into the system, this is an electron micrograph. You see these lamella here, these lamellar structures. This is where this is the membrane where the light harvesting systems are located in. Notice the scale also. So this is a core scale. And in water pseudomonas acidophila, for instance, you have this arrangement where light harvesting complex 2 is in so-called antenna complex, roughly 20 angstroms across, and it feeds energy to the LH1 complex, which again feeds it to the reaction center, which will then make an electron transfer across the membrane. So we will look at light harvesting in here. Let's put some numbers to the system. You see in the absorption spectrum, you have the QY absorption, which has been mentioned by Jeff. This is the bacteriochlorophylls, so the B800s, B800s are here, are isolated molecules, whereas the redshifted B850s are exotonically coupled, so redshifted. And then you have the weak QX absorption in the visible region and a strong, broad absorption from the carotenoids. So the carotenoids are essential to the light absorption in this system. And now what has to be done by this molecular machine is it has to assemble all the excitational energy into one state. And this is what this is about. So when you excite energy in the carotenoid, it goes to the optically allowed S2 state. S1 is optically forbidden by symmetry. And from there, it can hop to the B800 or directly to the B850. And approximately 51% of the absorbed energy does that. But in this particular complex, 49% undergoes internal conversion to the S1 state. So essentially is more or less lost for energy collection. And from there it goes further down to the ground state. There is some very weak coupling between S1 and the bacteriochlorophylls, which is not essential. And there are some excellent reviews here by Polivka and Sundström on these issues. So we have a natural system which is not optimal if you want to. It is a system that collects only 50% of the energy from the carotenoids to the final state. So what we will do now is we do simultaneously spectroscopy on both the lost channel, S1, internal conversion, and on the energy collecting, energy transfer state, B850QY. And we will now apply these newtons of spectroscopy.
Can I ask one question?
Sure.
What's the orientation of the carotenoids relative to the membrane? So is it fully embedded? Or?
So the membrane goes like this.
Yes.
And actually you see it better in this
Okay.
graph here. So the membrane is like that. So the carotenoids traverse the membrane if you want to.
Okay.
Well, they don't traverse it, but they are perpendicular to it.
Right. But they are actually parallel to the lipids then in the membrane, or they are
Yes.
outside?
But they are parallel to the lipids. But what you see here is they don't see much lipids because there is an inner wall, protein wall, and an outer protein wall that holds this assembly together and more or less screens the chromophores from the lipids. Okay, so when we allow the excitation pulse to assume any pulse shape within the given constraints by the laser system, this is what it looks like. We going from the transform limited, so the non-shaped pulse, we can achieve a 35% change of this ratio from internal conversion and energy transfer. So what we can do is we enhance the internal conversion. We increase the lost channel. This is what the pulse shape looks like. This is a frog trace from the experts. The essential thing here is you have a two-dimensional plot of the time axis and of the wavelength axis. It looks weird, it looks strange, but what is specific is that when you have the autocorrelation, so you just sum it all up on the time axis, you see this multipart structure. And in fact, this is the only feature that is recurring in different optimizations. So if you do one optimization and then another optimization, you will get a totally different frog trace, this or this, but what they always show is this multi-pulse pattern. And they achieve essentially the same change in the system performance. So you go from this 50 to 50 splitting of internal conversion and excitation energy transfer to 70 to 30.
So we enhance the energy?
No, we tried that and we couldn't do it. There are some reasons why this might be so. I'll come back to that. So our idea was, let's simplify things. If really this multi-pulse pattern is the only thing that is essential, we should do a clean multi-pulse. And this is what you can do. This pulse shaping is something that is done in Fourier space, so it is done in the wavelength space. And if you apply a spectral phase to a femtosecond pulse, so phi of omega, that is the sine function, looks like this. This is the spectral phase, and this is the spectral amplitude. Then, in time domain, which is shown below, you will go from a single femtosecond pulse to a femtosecond pulse sequence. It is a coherent pulse sequence, and now this parameter B, which is the spread of the sine phase function, controls the spread of these multipulses. We can now again look at what is the achievement of these multipulses, and now we get a rather clean picture. So this is a histogram of successive optimizations. So we see that most of them hit an modulation parameter B that is around 160 wave numbers. And if you compare this to a Raman spectrum of beta-carotene, which is not the same thing, but it's comparable, you will see that, yes, there are vibrational modes of the carotenoid in this region, and this is the important difference. We do not make a spectroscopy of all the modes that are there, but instead we look at which mode is essential for internal conversion. So what we have picked out here is a mode of 160 wave numbers, which does something to the internal conversion. It can enhance it. That's all we can say on a phenomenological level. Now, we must look also at energy dependence. Down here is the linear regime. And this is the linear regime where we have an enhancement of the internal conversion and a decrease in the energy transfer. If we now scale up excitation energy, by the way, the regime down here is around 10 to the 14 photons per square centimeter, then we see a behavior that is not fully understood, but the essential thing is indicated by these pink arrows here. Wherever we look, we always see the splitting of the energy flow. So we see that we can enhance the internal conversion more than the energy transfer. So we do have two effects here. We have a robust control of the energy flow, and in addition, what's indicated by these lines here, which are just a guide to the eye, we have some effects of saturation, so of energy. And these saturation had been addressed by the Amsterdam group. They can more or less understand why saturation comes into play here, but the essential thing is the splitting of the energy flow. Now, what is the reason? You do have a simple model that relates to these multipulse excitations for non-resonant excitation. So, meaning a excitation that is not resonant with two electronic states. It's a non-resonant infrared pulse, for instance. Then you have the excitation probability for a certain omega Rabi, so a certain Raman state. That's proportional to this integral, and when you integrate over these two electric fields, and you now have a phase that is a Raman pair phase. So you have one pulse going up, and then another part of the pulse going down to the Raman level. Then you will have interference of these sinusoidal phase modulations, leading to a modulation of this excitation probability or population that selects certain Raman levels. And this is a mechanism that has been well worked out by especially the Silverberg group. So Silverberg has done many, many nice experiments with non-resonant multipulse excitations. There is an alternative view which is maybe more intuitive, especially by Weiner. What does a multipulse do? You hit the system once, you wait some time, then you hit it again, you wait again some time, you hit it again. It's like having a kid on a swing So you just have to be resonant with the frequency of the system. And this is the same thing as saying that you have interference between Raman pulse pairs. So you hit the resonance of the system. So what may be happening here is, by having these 160 wave numbers, we selectively excite the system into a 160 wave number mode and not into all the others. So this may be it. From work on linear polyenes, we know that there is a conical intersection between the S2 and the S1 state, and we know that the Frank-Condon region is somewhat away, especially along the angle alternation coordinate. The angle alternation is in fact among these low frequency modes, which are in the range of 160 wave numbers. So we believe what we are doing here is we make this selective Raman excitation by this multi-pulse excitation, but at the same time, and this is something that nobody can calculate, unfortunately, at the same time we transfer this wave packet to the excited state such that going from the Frank-Condon region to the conic intersection is made easier. I don't have time to speak about the resonant case, where we do see not only selectivity but also enhancement. I want to speak shortly about some other methods that we can apply here. I said that we rely on Raman excitation in the ground state, so is there sufficient Raman excitation in carotenoids? What we do is we excite S2, so the only optically allowed state. Then we take away the population from the higher excited state with a second pulse, shown in pink here. And then we probe the remaining deactivation channels. And this is what it looks like. If you look at the absorption spectrum, here shown on lycopene in solution, you have the bleach of the ground state, and then you have here the S1 absorption region, which indeed is depleted by the action of this pulse, because we take away population from the S2 state. There's no population that can go to the S1 state, so this is diminished. And indeed, here where you would expect the signal of a hot ground state, of a Raman excited ground state, this second pulse that goes from the excited states does nothing. That's fine. We updated this now with more carotenoids, looking at all these artificial carotenoids, and it also looking at time dependence of this depletion action trace. And this absorption window here really does fit perfectly within a few femtoseconds to the fluorescence lifetime of the S2 state. So we are pretty sure that we really do what we think that we are doing. So this is the depletion from the S2 state, and never have we observed any change in the hot ground state region. And finally, if you look at two-dimensional traces of standard pump probe experiment wavelength over time, this is where the hot ground state sits. Some people call it S star, and this is again a hot debate in the community. The lifetime of this never changes, it's always 6 picoseconds, so we are pretty sure that we found this hot ground state. I want to mention just very shortly that this is not the full story. Carotenoids are much more complex than this. What we've been looking at right now is this part, but we know that by incorporation into the light harvesting complex, and this is the point that you referred to on the first day, yesterday, we do activate ultra-fast internal conversion intersystem crossing to the triplets. So it may be because the symmetry of the carotenoid is bent into a helix. It may be the neighboring proteins. It may also be the neighboring chlorophylls. We don't know that. But something completely changes the deactivation flow when you go from the solution to the light harvesting complex. You can see it here in the depletion pulses. You can pump energy from here to here and back again to these states. So this triangle really exists. We are pretty sure about that. Actually, there's even more. The doublet is also important, but we don't have to care about that now. I want to draw your attention and make some advertisement for very nice work by the Miller Group from Toronto. They looked at retinol in pachiorhodopsin, which undergoes an isomerization. You will notice that this is just 1/2 of a beta-carotene. So the system is related. This is what it looks like in the environment, and the essential torsional mode is 200 wave numbers here. They now applied the same coherent control shape pulse approach, and they find that they can not only achieve plus 20% of this isomerization, but also minus 20%. So they can both increase and decrease the rate. And if they look at the optimal pulses, they look complicated, but they have a recurrent feature, which is rather low frequency wave numbers, which are 230 wave numbers for the optimal excitation. And if you look at the transients at the same time, this is all just copied from the SI paper, you again see this modulation in the traces. So it seems that in this system also you can drive the isomerization by applying Raman excitation of these 200 wave number modes. So, summing up, we have seen that we do selective Raman excitation in the ground state and transfer this wave to excited states, where it either goes into atomic intersections of internal conversion in LH2, or if you look at the retinol work, into isomerization. We could only diminish the natural function, not enhance it. They could enhance both and diminish. And you can also look at correlations or connectivity in multi-dimensional states by using Frank-Condon windows for manipulation with third pulses. And that's it. Thank you.
Questions?
You mentioned that in the solid state, the carotenoids underwent efficient system crossing.
Right.
And is that important? Or, I mean, is that important in terms of losing the energy transfer? You said that you only get 50% of the energy transferred from the carotenoids to your corporate. Is that because you go to the triplet state, or is the fact that you go to the triplet state important that you actually get that energy transferred? Is it good or bad?
It is bad. So
why is it bad?
About 10% of the excitation energy go into the triplet, and that is part of the 50% that are not used for energy transfer for light harvesting. So it's a lost channel.
So why is it a lost channel? Is it because the triplet can't get transferred out of the system?
It cannot. No, but it is energetically too low. So you have transferred all the energy into heat.
Okay, so it's too low.
Yeah.
So that's interesting because I mean, in terms of all those orbits in the ring that you've got there, they have an absorption sort of around about 900 nanometers, which is pretty low. I mean, that's what around about 1 EV.
Yeah, but the natural function of this triplet is that it takes away the triplets from the chlorophyll system. So
it's even lower than the
So it does have a natural function, but not for light harvesting. It's a lost channel there.
Yeah.
Which may be one reason why the system evolved into this configuration, because it serves more than one functions.
Yes.
I probably didn't catch all of this because there was so much in one go. But you were looking at which motions or what was important to enhance the internal conversion.
Right.
And you mentioned something about a sort of 160 wave number. So something at 160 wave numbers is important and that enhances the internal conversion. have you any ideas what that is? Does that correspond in some way, I guess, like in a Retinal system, you've got the structural
Right.
isomerization.
Right. So in that case, the structure doesn't change, of course. So it's more or less fixed. But what we believe is this 160 wave number modes is an angle alternating mode. So when the carotenoid bends like this, which is in fact the excursion that you need to couple the 1BU plus and 2AG minus state. So this is the one that leads to the quantum intersection.
Yeah, okay.
We can't prove that, but we believe that this is it.
That's a quick question about why is it 50% energy efficiency transfer from the carotenoid to the chloroquine?
Oh, it's different in other bacteria. LH2 from Rhodopseudomonas acidophila has 50%, but the one from Rhodobacter sporoides has 90-something percent.
This doesn't sound like nature to me. I mean, why? It should be able to be more efficient. What's the term? It's the lifetime of the state, basically. The S2 state.
It's about the same. It's both 100 femtoseconds being diminished to 60 femtoseconds in the system. So both are very efficient and fast energy transfers.
So what's the difference between the two? I mean,
At different carotenoids.
they're just correct.
Yeah. So spheroidinone in Rhodobacter spheroides and the rhodopene leukocyte in
So it's energetic sort of different, or the lifetime?
right.
is-
They have different conjugation length, which of course shifts the entire energy scale.
So it's affecting the overlap.
You can guess so, yeah. I would guess so, yeah.
If memory serves, these molecules are symmetric, but the symmetry is thermal.
I'm sorry, can you speak up a
These
bit?
molecules are symmetric molecules, but if, as you said, the symmetry is broken by their shape or by the protein. If memory serves, the D1U states are ionic states, right? So you can align these in the membrane in the field, then perhaps you can tune the energy gap between that and the G state. And
Well, they are not.
this moon.
They are not ionic. There is a carotenoid called comes from Tannor. I forgot the name, but that one has important charge transfer states. These don't. So electric fields may not be so effective.
I have actually a similar question that Meredith had. What is this 160 number more? For example, if you look at the Tannor-Rice-Control or Case Nelson's impulsive stimulated excitation and bromide more, the key to the success of that scheme is heavily relied on the nature of this vibration more. It has to be relatively isolated, so that there is no strong vibrational decodiments. But it shows that this gamma spectrum of this carotenoid, which is relatively broad and almost continuous, there is no key in your spectrum at 160 rate number.
No,
So
that's the point.
this 160 rate number could be a sort of a combination of many different vibrational freedom. It's not just a simple portion of mode. Like,
Well, yes, it could be an overtone of one mode and
right. So if there is such strong anomaly couplings between many different vibrational freedom, is it really possible to put energy onto that mode?
Well, just coming back to the kid on the swing, if you push for the double frequency, it will still work.
That's a very nice picture if you were considering well-defined single oscillator.
Right.
The neural oscillator is more or less complicated than that. Right?
For instance, in the work from Toronto here, they also attribute, you can see it here, but there is a 390 wave number modulation in the pulse and 230. They say maybe it's just an overtone. It may also be another mode. That's something you can't really tell. You can't look at, I mean, it's not a 2D spectroscopy. You can't look at couplings between modes in that approach. But you get out some numbers for them out.
Well, I think we'll have to stop there and move on to the last talk so we can keep on time. Thank you again.